Welcome to the tutorial 1A of the methods of transportation econometrics and statistics. So it's called 1A because due to actual reasons, this problem sheet is interspersed between the regular tutorials 1 and 2. So we will begin with the first problem setting. That's the simplest infection spread model, the SI model. SI stands for susceptible and infected, and the model equation is just a simple equation. It's just the change of rate of the fraction of infected, so fraction between 0 and 1, equals the infection rate, this is the model parameter, times the number of infected itself, so that would be an exponential curve, but then it gets saturated after some time, and that's the factor 1 minus I. So obviously if I equals 1, that means everybody is infected, there's no further infection possible, and the change of rate equals 0. So now the first problem A. We should just show that this function, which is basically also called sigmoid function, it looks S-shaped, is a solution to this equation 1. And also for the initial infection percentage I from 0 equal 0.5. So we can show the first directly, because just setting t equals 0, then we have exponential 0, which is 1, divided by 1 plus exponential 0, 1 plus 1, so we have 1 divided by 2, which is 0.5. In order to, but that's only the initial condition. In order to see if this in fact solves this, one has to insert this into the left and the right hand side of this equation. So we do it first the left hand side. The left hand side is a time derivative, it means a derivative, and here we because with the ansatz was a fraction, so we have to use the ratio rule. That means if we have a ratio of functions u and v, which should be derived with respect to the independent variable, that's just the dash. It can be x or t. If there's only one independent variable, you can just write the dash as an abbreviation, and that's just a rule you probably know from school, u dash v minus v dash u divided by v squared. So we just insert it. U was the numerator, it was exponential beta t, and the denominator was 1 plus exponential beta t. So u dash is just beta exponential beta t times v unchanged is this factor, minus v derived, that's just beta exponential beta t times the unchanged u. This gives exponential to the minus to a 2 times beta as t, and that's just a squared denominator. Now we can simplify it and just get this expression. We do the same with the right hand side, just inserting the I from t, that means for exponential beta t divided by this denominator, times 1 minus the ansatz. Now, because we want to have the same denominator as here, we put everything to the common denominator 1 plus exponential beta t squared. That means we have to multiply the first factor with this, and the second factor is just the same. And now we see that the left hand side and the right hand side is the same. So we are done. We have shown that this in fact satisfied the differential equation, and the initial conditions we have already shown that because I from 0 equals 0.5. Generally, with a so-called differential equation of first order, you have one free variable, which obviously here is the initial condition. You could just start with 1% or 1 per mil of the fraction infected, then of course you get another function, but it always looks similar. Now we go to the second problem of this tutorial. This is the SIR model. It's an extension of the SI model, which makes it much more realistic. It adds a third category of a third compartment of persons. Besides the susceptible and the infected, they are also the recovered. The property of the recovered is that they are no longer contagious. So there's only an infection period, which is just the period of the people being in the I state. So the model is, the first model is just like in the SI model. The second model, the first time is also like in the SI model, it's just what is subtracted here is added here, but then again is subtracted the transition from the infected to the recovery state with a new model parameter gamma, and then of course in order to balance the rate of change of the fraction of recovered is plus this recovery rate times the fraction of infected. So the first problem is to show that the sum of these three is constant and can be set equal to 1. To see if it is constant is easy. Just take the balance of all the three equations. So take a balance line and then just take the addition. Then we have on the left hand side the sum of the time derivatives of s plus I plus r. On the right hand side we have minus this term plus this term cancels, and this term cancels as well. So all the two rates, the two transition rates cancel each other. So the right hand side is 0. So the time derivative of the sum is 0. That means the sum itself can have any value, and we can set it to any value we like, but in order to give s plus I plus r the meaning of fractions of the population, we set it to 1. So that means any person in the population can have exactly one of these three statuses, S or I or R. So that was the first subtask, or A. So now we argue that the third equation for R is not really needed and can be calculated afterwards. How can we see this? Here we just check if this equation with this model suits the general concept of econometrics. It means normal model, linked model, chained model, and feedback model. And here we see that it's basically a model chaining. And also the first two are model linking, because S depends also on I, and I depends on S, but on nothing else. So that means this is a linked model in itself, the first two equations, and the third equation is just chained to the first equation, but only in one direction. So that means we can completely calculate the first two equations and then just calculate afterwards the rate of recovered over time. So that's basically model linking. The first two models are linked to the last equation. So that was B. Now we come to C. Now we want to calculate something. Consider the beginning of the infection, where at the beginning, obviously is the fraction of infected much less than 1. It must be greater 0, because otherwise the infection cannot start. And that also means we have no recovered person yet. That means the number of susceptibles 1 minus I is essentially 1. So let's now consider the middle equation of a model. That is this equation. And here we see that if we set I is a small number, here also is I. So if we set the exact value of S equal 1 minus I, we would have I squared here. But because I is already small, I squared would be much smaller, so we can neglect it. So we can just set S here equal to 1. And then we have just the equation containing only di dt equals beta I minus gamma I. So this is this equation, and here we see that it's just we can write the two terms together. So we have just a prefactor beta minus gamma I. So we have the rate of change of I is just beta minus gamma times I itself. So this is again the classical model for unlimited growth, this times with a growth rate beta minus gamma. You know from the lecture that the number of people infected by a single infected, the R0, provided there's not yet any immunity, is given by beta minus gamma. So that means only beta divided by gamma. So that means only if beta divided by gamma is greater than 1, then the growth rate here is positive. So we can also say it's gamma times R minus 1. So that's also tells the crucial importance of the reproduction number R0. So now we go to the fourth sub-question. So show that any solution S equals S0 equals constant and any constant recover number is a solution provided that the number of infections is 0. That's more or less this means that the infection is dead because there's not any infected, and one should just show that this is a solution for any susceptible number and any recovery rate with this relation. So let's look at this. So just let's insert I into the SIR equation and set all the time derivatives to 0 because we want a steady state solution, and then if we insert this we obtain 3 trivial identities. So that shows that any combination with I equals 0 is a solution. And in order to obtain the meaning of a fraction, we set the sum equal to 1. So that means we have S from t equals S0 is constant, I equals 0, and R from t is R0 minus is 1 minus S0 is constant. So this is a steady state solution. Now, of course, this is more or less trivial, but not trivial is under which conditions a new infection may be brought in elsewhere by some traveler, so reintroduced. So it's reintroduced at time t equals 0 from elsewhere, and now we have a tiny fraction I tilde of new infections, and so at time 0 we have a situation a tiny fraction of the susceptibles is infected, so the new initial condition is the steady state minus the small new infection, and the infection rate, because in the steady state it was 0, is just the small new infected, and at the initial the recovery rate is still the same. It's like the steady state. So generally we have just this is just the initial conditions. So generally we introduce the small quantities with a tilde and they act as a perturbation. So generally we have S is S0 minus the small perturbation, infection rate is just the small perturbation, and also recovery rate is R0 plus the small perturbation. And now we want to show under which conditions this new infection will die out or trigger a new epidemic wave. And also we want to express the found condition in terms of the initial growth rate R0. So there's also a hint because we want only to look at the beginning. We are not interested in the situation where the small initial perturbation grows to a sizable amount, so we can ignore all products of quantities with a tilde, because they are much smaller than quantities with a single tilde. And in this I equation, we of course, that is this middle equation, there's always at least one tilde unity quantity, because there's always equation always contains I. So let's just insert the assumption into this equation. That is I equals just tilde I, it's also beta tilde I, and because this S is of course S0 plus tilde S, but we neglect products, so it's just this tilde S equals just S0. And if we insert this, we get following results. Then we get just this new equation. So it's just the time derivative, of course, is also only a small amount, because I0 was 0. And here we have just again an equation for an unlimited growth, and this times with a growth rate beta S0 minus gamma. So this is just an exponential growth, so you can verify just by inserting this into this, that this is a solution, so we have just an exponential growth. So what does this mean? A critical point is this new effective growth rate positive or negative? If it is positive, the introduced new infection will start a new infection wave. If it's 0 or negative, then it just dies away. That means it will not start a new wave. So we have just the condition beta S0 minus gamma is greater than 0 for a new wave, and we are safe if this is less than 0, such as here. So that means besides the parameters beta and gamma, this new effective growth rate depends on the initial fraction of susceptibles. So that means, because both beta and gamma are positive, that means if this S0 is sufficiently low, there are less than a maximum number of susceptibles left, then a new infection will just die out. And of course, if lambda is greater than 0, it will trigger a new wave. Now we introduce the initial reproduction number beta gamma, and then we just reformulate this condition. So criterion for an onset of a new wave is just this effective growth rate is R0 S0 minus 1 times gamma greater than 0. Because gamma is positive, it just means this inner factor must be positive. Note that for R0 less than 1, this is never fulfilled, because the maximum of S0, if everybody is susceptible, is 1. So if R0 is less than 1, this factor can never be a positive. It will always be negative. That means the growth rate will always be negative. If, for example, as in the lecture examples, R0 equals 2, then the new wave will start if R0 is greater than 1/2. Notice that in this, if you have a big wave already running, until it died out with R0, with the susceptible fraction will be much lower than with S0. So now we come to the third problem of this tutorial. It's a discussion about tests. With tests, I do not mean statistical tests, but I mean physical tests with two outcomes. So it's not related only to COVID-19, but to any such binary physical tests. In reality, these perfects are not ideal but real. That means they do not reflect reality perfectly. If it were perfect tests, then any true outcome in reality would test also positive, and any false outcome in reality would test non-positive or false. In reality, neither outcome can be tested perfectly. So we have a test has a certain sensitivity and a certain specificity. Sensitivity means if in reality a person is infected, then not every such infection is detected by the test, but there's only with a sensitivity rate 1 minus alpha, and obviously alpha itself in this times 2% is the detection error. That means 2% of the ill people will not detected by this test. In addition, there's a certain specificity. It means because you only test people where you do not know if they are ill or not, so they may also be healthy, at least not having COVID-19. And then the specificity means only the rate 1 minus beta of healthy people are checked as negative. That means the test does not say they are positive. The complementary probability beta, that's the so-called false positive rate. That means that the test says this person has COVID-19, although in reality it doesn't have. And there's a third crucial quantity which is relevant for the discussion. That's a so-called incidence. That is in the population. That means in a basic population, the probability that of having COVID-19. This problem is about these three figures. And so we have a small incidence. That means only 1% of the people have are infected just now, but not yet tested, and now we test them. So now to the problems. First, explain the meaning of alpha and beta. Basically, we have already done so. Alpha is just the detection error. That means the error that a ill person is not detected as such. And beta is the false positive errors. That means a healthy person is erroneously detected as having COVID-19. So, and you also, this alpha and beta, by the way, this beta has nothing to do with the rates of the SI and SIR models, but it relates to the alpha and beta error. And that means errors of the first and second kind. And under which null hypothesis alpha and beta would be errors of the first and second kind. So let's look at this. So let's say the null hypothesis the person is infected. Then error of the first kind is the probability that the null hypothesis is rejected, although it is true. And obviously the person is infected to test if a real infected person tests positive. That's of course the sensitivity issue. That means alpha. That means the error that a COVID-19 person is not detected as such is an error of first kind if the null hypothesis is that the person is infected. And conversely, the beta error, the false positive rate, is the probability that H0 is not rejected under the condition that H0 is also is false. That is a false positive. So that was problem part A. Now let's come to problem part B. So we in this type of problems where there are conditional probabilities, and notice that alpha and beta is nothing else as conditional probabilities, and we want to have the reverse conditional probabilities. The probability that a positively tested person is ill that is always a case for a theorem of bias. And this theorem of bias can be most easily and intuitively analyzed by drawing a probability tree of a situation. So we started with a distinction infected, not infected, and then branching into tested positive and negative. So let's do this. So we started with a person of the population, and the problem statement says with a probability p of 1%, this person is infected. So that is the high level branch is about reality. And with a converse probability 1 minus p, the person is not infected because it's a binary outcome. Now come the imperfect tests. Remember, infected person, that's about the sensitivity, that means about the alphas. So it's an infected person is tested positive with the sensitivity of 1 minus alpha, which is 99% in this 98% in this case, and it is erroneously tested negative with error of first kind alpha, provided that the null hypothesis is this person is infected. Now the other branch is about non-infected person, that means it relates to the specificity beta. So this is the false positive, and this is correctly identified as being negative. So this is a tree diagram, and basically with this tree diagram you can also easily answer the last sub-problem. So determine the expected fraction of positive tests. And then the conditional probabilities that a positively tested person is infected and a negatively tested person is not infected. That's basically what you want to know. You are tested positive. What is your probability of being COVID-19 infected? And if you are not tested negative, what is your probability now to have this COVID-19, provided that you got a negative test? So let's answer the first. That is just the unconditional probability that a positivity test that the test becomes positive. Basically, if you have this probability tree, you have just to count all the branches which with a positive outcome. So this is this branch and this branch, and then the combined probability is just the product of all probabilities when going to this tree. So we have two trajectories through this tree, this one and this one. Here we have a probability p times 1 minus alpha, this is this one, and here we have a probability 1 minus p times beta, this is this one. And if you insert the numbers, p equals 0.01, alpha equals 2% and beta equals 1%, we get 1.97%. Notice that the probability of a positive outcome is nearly double as high as the real probability of being infected. That means the number of positive tests is about twice the number of infected persons. So that was the first question. Then we want, so if you are have a positive outcome, we want to know the probability that you are infected if you have a positive test. So the sentence of Bias, the theorem of Bias says this is just the product of conditional probabilities in the numerator and the unconditional probabilities for a positive test, which just calculated in the denominator. You can also see it with a probability tree. So the condition is positive test. That means we restrict here to all the branches with positive outcomes. It's basically this branch and this branch. And when we want the probability that if you have a positive outcome, you are infected, then you have just to take the ratio of this branch divided by the sum of this branch and this branch. And this sum we have already calculated to be 1.97%. And basically this is also the sentence of Bias said. So the probability you are infected positive is just the first branch, p1 minus alpha. Remember, this is p times 1 minus alpha, and the denominator is just p times 1 minus alpha plus 1 minus p plus times beta, and that is this. And then you get nearly 50%. That means if you have a positive test, you are only your probability of really having COVID-19 is just 50%. The reason why this is so low is because of a low incidence. Of course, the test has gives some information because it has increased the unconditional incidence of 1% to 49.7%. So we expect that if you have a negative outcome, your 1% incidence is reduced much more, because obviously this test gives information. And how we do it? Just in the same way, we just count the branches. Here we need all the branches with a negative outcome. And so that means we name this branch and this branch. And we want to know the probability that you are not infected, provided that you are tested negative. That means you have to take a ratio of this branch divided by the sum of this branch and of this branch. So the numerator is 1 minus p times 1 minus beta. This. And the denominator is the same branch plus the other branch, which is p times alpha. So, and if you insert the number, you get 99.98%. That means if you have a negative test, you can be pretty sure that you do not have COVID-19, because your chance of having this is has reduced from 1% to 0.02%. So, many thanks for watching this tutorial.